Question 3 from the 2012 Level 1 Electricity and Electromagnetism. The bouncing toy, and we've got a diagram below showing the design of a bouncing ball toy. The soft iron ball rests between the two fixed metal wedges. There's the ball, there's the wedges, and the ball is free to move up and down the metal wedges. The solenoid is the coil there, and the switch are connected to in series to a battery, so one loop all the way around to the battery. Looking at the circuit, I'm just predicting what's going to happen. When you close the switch, the solenoid will have current running through it, which will cause a magnetic field. That magnetic field will induce magnetic poles in the soft iron ball, causing it to jump up to the solenoid. As soon as the soft iron ball jumps up, it's going to break the circuit, so there's no longer going to be current flowing through those metal wedges, which means there's no longer going to be magnet in the solenoid. Magnetic field lines produced in the solenoid, so there'll be nothing attracting the soft iron ball, so it'll drop back down. As soon as it drops back down, it closes the circuit again, and then you have magnetic field and the ball is going to jump up. So I'm sure there's going to be an explanation of how to do that. Let's just move on and see. A, the diagram shows the direction of the current through the solenoid when the switch is turned on. On the diagram below, use the letters north and south to mark the north and south poles of the solenoid. Okay, so the current's going in behind. We're getting into part 2 of this as well, but we're going to use our right-hand grip rule to work out the direction of the magnetic field. So there's two ways we could apply it. We could apply it individually to each of the individual wires, or we could use it to cover the whole solenoid itself. So if I use it for the solenoid itself, and then we can double check using individual wires, my fingers, 4 fingers of my right hand, are going to be the current going in behind the coil and coming out of the page on the left hand side. So if we look at it this way, the current's going out and around that way. That means my thumb pointing upwards gives us the direction of the north. So we're going to have north up here and south up here. If we were drawing the magnetic field lines, which I'll just briefly draw in red, north to south, like so. Okay, with more coming out that don't necessarily meet arrows going into the south, coming out of the north. So describe the rule we've used to identify the north and south poles. We did that. If I wanted to do a double check on just a single piece of the wire, if we consider the wire going around the back, initially where the current is going in, so let's consider that the current. If we were to use the right hand grip rule on that, with our thumb being the direction of flow of positive current, conventional current, and our fingers going out and down the back, that means on the front side we would have magnetic field lines coming up, and then it would curl around and go down on the back side. So front side up, down on the back side. Okay, and that matches what we've got here. If we put all of those lines together, we're going to have, remember this is the behind part of the coil, we would then have the wire coming around in the front, and that's going to cause it to go in the other direction, but it's actually the same direction, so you've got a magnetic field coming up and then down the front, which is out the outside, and that matches what we've got there. Okay, so that's pretty clear and comprehensive. 2 forms of the right hand rule, it's good to know both. One of them is called the right hand screw rule, usually to do with the solenoids, and the right hand grip rule to do with individual current flow through an individual wire. That's in physics anyway, and level 1 science is a little bit inconsistent from what I've read. Anyway, moving on, describe and explain what the ball does when the switch is turned on. So describing, it's going to bounce up, and then it's going to drop down. It's going to bounce up, then it's going to drop down. It's not actually bouncing, and it appears to be bouncing. It's going to be attracted towards the solenoid. So that's the describe. Okay? The explain is that the solid iron ball completes the circuit where those wedges are. So when it touches down on it, it touches those 2 wedges, makes the current allows the current to flow, which means there'll be current flowing in the coil. As I said before, that's going to induce magnetic field in the coil. That's going to induce magnetism in the soft iron core, which will then be attracted toward the coil. If we want to get really specific, we saw that it was a north and a south for the solenoid. That means the top of the ball will become north, and south for the bottom. So the north will be attracted to the south, lifting it up, They will break the circuit as it comes out, and there's no longer current flowing in the circuit, so the magnetic field in the coil collapses and it drops back down. Once it drops back down, it closes the circuit again, reintroduces the magnetic field, lifts up the iron ball, cuts the circuit, cuts the field, and repeats. Okay, I've gone on for too long about that. See, the soft iron ball is replaced with a similar sized aluminium ball. I'll explain what the ball does now when the switch is turned on. It does nothing, because aluminium is not magnetic. Okay, definitely not ferromagnetic. Does not produce temporary magnetism in the presence of a magnetic field. D. Number of turns on the solenoid is doubled, so 2 times the number of turns. The length of the solenoid is unchanged, and the same current passes through the coil. So the same current is the same, and the length is the same. State how this affects the strength of the magnetic field, B, and explain your answer. So the statement is it's going to double the magnetic field strength. That's because you've got double the turns, because remember each turn contributes to the magnetic field. If we're looking at the side view of each of the wires going through, each individual wire with current going through, the dot means it's coming out of the page. This is like half of the coil with the other half current going into the page there. So each wire has its own magnetic field coming around, and they all just add up to produce one magnetic field. And if you double the amount of wires, even if you're keeping it in the same length, so maybe you're winding extra wires around the outside but they're still going in the same direction, you're just going to add extra field lines. So you're going to make the magnetic field stronger. So the length doesn't affect it, because the length has got nothing to do with how the magnetic field strength is produced. I guess if you were to spread out the wires, so you had twice the length, your magnetic field strength would remain the same, except it would just be longer. Okay, so magnetic field strength, the way of thinking about it, is the amount of magnetic field lines through a cut section, a cross section of space. And that's all for that question.